This button. Okay. So it's a question about studying. You can either study a lot, a little, or none. They give you some cryptic information, and they ask you about passing or failing the midterm. What would you try? How would you organize all this stuff? I think this is the hard part of word problems, right? There's like all these things, and you've got to like mentally organize what you have, like what you're given in the problem. You've got to mentally organize what you want to find. In this case, we want to know the chance that the student passes the midterm. You've got to organize it all. That's the hard part. And one of the techniques we did helps you organize this type of information. Well, let's see if you guys know which one that is. Reveal counts. Okay, here we go. Ooh, okay, this is great. So there's lots of little words throughout. The big words are probability, and I see tree with a lowercase t or tree with a capital T. So very good. That's what I would do as well. Probability tree. Some people call that a probability diagram. That's the thing you want to do. In smaller letters, we have Venn. I will show you that actually a probability tree and a Venn diagram are kind of the same thing. There's like a little bit different ways of visualizing the same thing. This one is perfectly set up for a probability tree. You could also do a Venn diagram. So let's do it. Let's organize what we have and what we want and solve the problem. And once again, if you think this problem is easy, please try to do it and then, see if you have the answer before me. Okay, so here we go. This is a different class. Okay, let's make a new note here. Okay, and let me get the text of the question correct. All right. So this is me copying and pasting the problem into our little blackboard. So when I copy the details over, they are not miscopied. Okay. So I think it's always helpful in any class to, anytime you have some kind of like real life problem like this, real life in quotes, you have given and what you want, right? What you have and what you want. Okay, actually, given is too fancy of a word for me. Let's do have. This is what I have. This is what I want. And you must chart a path from what you have to what you want. What do we want? We want to know the probability. It says the chance of passing the midterm. We know that means a probability. So it's the probability of passing the midterm. That is some kind of event. I'm going to give that event a name so I can talk about it. I'm going to call it G-pass. G-pass. G stands for grade. G-pass means the event that your grade was a pass. So these are things in my universe, in my little sandbox of the world over here. These are my stuff. And I have some events. Events. What do I got? I got G-pass. That's the event. You pass the midterm? You pass. Oh, sorry, not you, the student. Oh, my mistake. Student. Passes midterm. So I put it between curly brackets so that I'm like, hey, this is an event. It's a subset of the probability space. The other events, what other events are going on here? I got G fail. That's that you don't pass. Student fails. Okay? And G pass and G fail, those are two different events. We know that these are complements, right? If you don't pass, what's the opposite of passing? Then you must have failed. If you don't fail, you must have passed. So these are complements. That's the kind of thing we did in the first week. Complements. Complements. So G pass C equals G fail. Maybe this will come up at some point. Maybe not. But good to know. So if we know one, we sort of know the other one is the opposite. Very good. There's some other events in this universe over here of this problem. There's studying a little, studying none, and studying a lot. Let's give those names as well. S. Let's call them S a lot. Okay. You might have noticed there's no space in a lot. In real life, there's a space in a lot. In this problem, there's no space in a lot. Don't be confused. Okay. S a lot. You study a lot. I could never remember if there's a space or not, except there's this amazing comic where there's an allot, and it's like an animal. So this is the allot. This is like what they look like. This This is a lot. A study a lot. Oh, it should have a book. Okay. Hold on. So an a lot is this type of animal, and they come in all sorts of different shapes. This one is a study a lot. Okay, I'm going to stop. Study a lot. What else we got? Study none and study a little. A little. If you've never seen this comic, you must look it up. That's your homework. Okay. Study none. Study a little. Okay. So those are 3 other events. So our universe has 5 different events in it. And the thing about probability that makes it tricky is the events can be organized in all sorts of weird ways. So like G pass and G fail, we know they're complements. Kind of like the world is divided into 2 halves, the pass universe and the fail universe. But we have this other complicated stuff. These ones, none of these are complements of each other, but all 3 of them together, there is a special word that sometimes gets used. Again, one of those special math words that doesn't mean what you think it means in real life. Did anybody pick up on the special word that these 3 together are? Yeah.
Mutually exclusive?
Mutually exclusive. They are mutually exclusive. Mutually exclusive means there's no overlap. And in fact, any 2 of them are mutually exclusive. So like, you can't study a lot and study none. There's no way to do both. Any 2 of these are mutually exclusive. But there's one special word. So let me write that down, because that is correct. Let's do that. So they are mutually exclusive, aka disjoint. Exclusive. That's also known as disjoint, which I won't make any jokes about. Okay. So these 3, they are mutually exclusive. They are disjoint. Any pair of them is mutually exclusive and disjoint. But all 3 of them together have something special that is, you can say beyond just saying they're mutually exclusive or disjoint. So mutually exclusive or disjoint says something about the overlap. There's no overlap between them. The thing I'm going for says something about what do you get when you do all of them together. So this is no overlaps. No overlaps. AKA A intersect B is the empty set. And the thing I'm talking about is their union, something about their union. There's another special thing, the special thing, and it involves their union. S a lot. Union S none. Union S a little. There's something special about this. That's this one or this one or this one. Yeah?
I don't know what to call it, but it has 100% probability.
That is a better name for what it is, because the actual name is really silly. But this is, together, they have 100% probability. So together, they are everything. Everything. So that is the observation, is that either this one happens, or that one happens, or this other one happens, and there's no like secret 4th possibility. So together, they have a 100% chance of happening. Just the question is, which one happened? Out of the 3, which one happened? And the name that sometimes comes up for this in probability is exhaustive. Exhaustive. Or exhausting. I guess the whole class on the whole is exhausting. These 3 events are exhaustive. Why is it called exhaustive? It's like you've used up the entire probability space, right? There's nothing left over after these 3. It has all been exhausted. That's why it's called that. But the idea that they're all together, they are the entire sample space S. Altogether, they have a 100% probability. This is a nice idea. And it kind of is like the generalization of complements. Complements cover everything when there's 2 of them. This is covering everything, but there's more than 2 of them. All right. I think this has been said a few times in the class, but we never defined it. Now you know what it's called. Okay. All right. So now we have all the setup. We have all the things in my little sandbox over here. What is given in the problem are relationships between these sets, between these events. And depending on the problem, you'll have different weird relationships between these. In this particular case, they gave us some information. They gave us the conditional probabilities. So I think they told us at the beginning over here, they said, if you study a little, then you pass with 80% chance. If you study a little, you pass with 80% chance. That is a conditional probability. So the person who wrote the question told us a conditional probability, but as a sentence, right? So if you study a little bit, then your chance of passing the midterm is 80%. That says given that you studied a little bit, your chance of passing is 80%. That's a conditional probability statement. So the probability of your grade being a pass given your studying is a little is 80%. Okay, 80% also known as the number 0.8. Those are the same thing. There's a few like this. So there's probability of G pass given S a lot, and I think it's 90%, 0.9. And there's the probability above it is G pass given S none, no studying, is 50%. So they gave us those things. And then they also gave us just the flat out chances of none, a little, and a lot, which were 20, 50, and 30%. So they said the probability of S none is 20, 0.2, P S a little was 0.5, and P of S a lot was 0.3. So these were the things that were given sort of in the problem. And the thing we want to do is combine them to get the probability of passing. And you could do this entirely like on, with just letters and like algebra and like using probability rules, but that's what a probability tree does. A probability tree just organizes this kind of information to something where you can get this kind of information. Everybody with me so far? Any questions or comments? Yeah.
Would it be, given the fact that we studied none, our chance of passing is 0.2?
The 0.2 is here, which is there is a 20% chance they study none. So that's the probability of S none. The conditional probabilities are all in sentences that start with the word if. If the thing you're given happens, then the thing you're interested in has a certain chance. So the if is the keyword for thinking of given. You could rephrase these as given. It would be a little bit awkward in real life. But I guess it is something that people say. But yeah, that is an important part of the question. That's why I'm taking my time with this, is how do you interpret the words into math things? Yeah, great question. Anyone else? Okay, yeah.
So if that is conditional probability, then what is the fact about
These ones? So there's 3 conditional probabilities, and there's 3 just like outright probabilities, right? A conditional probability is like if you're given a specific piece of information and you're only looking within that piece, and these probabilities are the entire probability space. So like these S none, S a little, and S a lot, we just know their total values through the whole probability space. You'll see that these total things will be the first layer in our probability tree, and then these will be the second layer, depending on what happened in the first layer. So that's how probability trees combine this stuff. We'll also see it visually with a Venn diagram, so maybe it'll make more sense then, too, if it doesn't yet. Yeah?
I'm not sure if this method answers the question I was looking for.
Yeah.
The probability part says that if they don't study,
Yeah.
half their pass rate is 50, and then it has a 20% chance of happening.
Yeah.
If you multiply those 2 percentages, that would be the probability for both of them happening.
That's right, yeah. And you'll see that when we do the probability tree, when you're going down the probability tree and you're multiplying things along the branches, that's exactly what you're doing. So what you're describing is the rules for the probability tree, or the rule for conditional probability in reverse. That is the rule we're going to use, which is that the probability of A and B is the probability of A times the probability of B given A. It also works the other way. You can do them in any order. Probability of B times the probability of A given B. And you'll see that in the probability tree, that's exactly going down one of the branches, where the first probability is the first branch, and the second is the second branch. Yeah. So you got it right. Yeah, this is like if you're going to do it with only algebra and no pictures, like if you are a computer program that only speaks letters, this is like you would just do a bunch of equations like this, and it's technically correct. Okay, let's draw the tree. I keep talking about the tree. So here's the tree. Here is the first thing that can happen. And I'm organizing the tree based on what I have. So I see that it goes S none, S a little, S a lot. These are exhaustive. One of them has got to happen. That's a great candidate to put in the first layer of my tree. You could try to do the tree the other way with like pass and fail first. Like that is a tree you could do, but we just don't have the information to do it yet. So let's do it in a way that's convenient for us. We're starting with either you study none, a little, or a lot. None, a little, or a lot. Those are the three things that can happen. And we were told they're absolute probabilities. So the probability, I guess let me mark it around here. So these are events, and their probabilities are given, I think it was 20, 50, 30.3. Okay. So that's the first layer of the tree. And then in each layer of the tree, one of two things happens. Either you pass or you fail. So in the next layer of the tree, let me try to line them up a little bit. So I guess there's, you can either pass or you can fail. Pass, fail, pass, fail. And we know the conditional probabilities. And that's why these branches are marked, because we already know what happened in the first one, so we can use the conditional probabilities. So in this one, I'm going to do probability of pass, G pass given S none. We know what that is. That was 0.5. And we can also use the fact that pass and fail are complements. So either you passed or you failed. So if there's 50% chance of going down that branch, there must be a 50% chance of going down this branch, right? So because they're complements, I can infer this. Because S pass, S fail are complementary. Okay, I'm only going to write that once. I'll use it a bunch of times. And I'll write it in super tiny letters. Okay, 0.5, 0.5. Similarly, if you just fill in all the stuff we have, what else do we have? We have 80% one way, 0.8 one way, 0.2 the other way, 0.9 one way, so 0.1 the other way. And this organizes all our information. The conditional probabilities go in the second layer, or we're conditioning on what happened in the first layer. So that's our probability tree. Questions or comments about the tree? You might say trees don't go sideways. They go up and down. Well, my tree went sideways. Okay. Now the question, can you find the probability? So find the probability. This is the one trick you can fall for, is make sure you go over all the branches, right? We're trying to find the probability of passing outright. And the probability of passing outright, there's all sorts of different ways it can happen. It can happen up here. This is passing and the none happening. This is passing and a little happening. This is passing and a lot happening. All of those are valid ways. So you got to sum over all the paths. There's this path, and this path. So the probability overall to pass, that your grade is a pass, is a sum over all of these ways. So let's write it out. There's pass given you study none times the probability of none. That is the very tippy top branch. Plus there's the middle branch of pass given a little times the probability of S a little. Plus there's the probability to pass given S a lot times the probability of S a lot. Okay. So this is, logically, this is summing over the branches of the tree. Sometimes this rule gets a cool name. Probability theory has some cool names. This rule that we used is sometimes called the law of total probability. Law, which sounds like a badass thing you would say to somebody before you send them to jail. Law of total probability. You must go to jail because of the law of total probability. And basically it works because these events are exhaustive. We know one of these has to happen, and then you can do this kind of conditioning thing. More on that later when we do things with random variables later in the course. Okay, so I'm just writing out that simple idea, sum over these things. Now I'm going to evaluate them. This one, pass given none, was 0.5. The probability of none was 0.2. Pass given a little, that was 0.8. plus the probability of a little was 0.5. That's a multiplication. Plus, last but not least, 0.9 if you study a lot, but that only happens with 30% chance. So those are the three branches coming together to give the probability you want. Okay. You could add this up and do it, but in the interest of time, I'll just leave it like that. It's perfectly fine for what we want. It's the sum of these numbers. Questions or comments about this thing? Yeah. Yeah, so the law of total probability just says if you want to know one event, you can split that event up into any collection of things that are exhaustive. And it really, in our picture, it just means if you have a probability tree and you want to know some event, then add up over all the branches of the tree. That's all it says in our picture. Yeah, so you don't need to know what this means. I'm not going to ask you a test question, what does this mean or something, but just to give you the name so when you see it later, maybe it'll ring a bell. Yeah?
If this is an exam question, would you have to kind of show all this work? Or let's just say I just did it last time.
Yeah, this is a great question. If it was like a short answer, and we'll try to be really clear on like what we're grading. If it was like a short answer and we said, get the right number at the end, and you did this, then full marks. There might be a different type of question where we say, please explain why, and then we would want to see more explanation why. And we'll try to be clear about which one is which. Yeah? Yeah, that would be fine. Like I think you can also just like have these equations and not the picture. The reason the picture is good is because it helps your brain understand what the equations mean. But if your brain already knows what the equations mean, then you can skip the picture. Yeah, great questions. Anyone else? Okay, I'm going to draw the same thing. We drew it with a probability tree. I'm going to draw it one slightly different way, which is the Venn diagram, or the Venn-like diagram. And it's exactly the same information. There's nothing new or different. It's just a different way of representing it that maybe is helpful. So here's what I'm going to do. I'm going to take my probability space, and I'm going to think of it as a big rectangle. So here's my probability space. It's a big rectangle. Okay, this is a terrible rectangle. We'll try it one more time. Make a slightly better rectangle. Okay, so this is the big probability space S. S contains everything. That's the sample space. Some people call it omega, which is a cool name too. I'm going to split it into three things. A little, a lot, or none, just like we did. And I'm going to do the splitting on the x-axis. So let's see. Yeah, the total area should be 1. This should be like a square. Let's make it a square. Okay. So I'm going to think of this as kind of a 1-by-1 square. So here's me thinking. And of course, these dimensions don't actually matter, but I'm thinking about a 1-by-1 square, like 1 meter by 1 meter or something, okay? And then I'm going to put a lot, a little, or none, these three events on the sort of x-axis. So none can be this one. None is like this. S none. S a little. Or S a lot. Okay, and I kind of want it, if I was a better drawer, this one would be height 0.2, this one would be height 0.5, and this one would be height 0.3. If I was good at drawing, I could draw it to scale perfectly. I'm not great at drawing. I try my best. And the events are like the entire rectangle over here. So S none is this rectangle. All of this is S none. This is S a little, is this bigger rectangle. And on the bottom is S a lot, is that medium-sized rectangle on the bottom. And if you have things set up right, if it's a 1-by-1 square, and the height of these things is 0.2, 0.5, and 0.3, then the area of the rectangles is 0.2, 0.3, and 0.5. So I'm kind of thinking of area in my little thinking bubble. Let's add probability is like area, right? And that's what's nice about this kind of picture, and what's nice about Venn diagrams, is your brain is good at area, right? Like when you were a caveman, you had a lot of fights with your caveman neighbors about who gets the caveman spot near the, whatever. You had fights about area. And now you're using that part of your brain. Like areas, at least to me, are kind of intuitive. So that's fine. I haven't done anything super cool yet. The cool thing is coming now. You can draw the conditional probabilities on the x-axis. So the pass-fail things, you can split them like this. So here's the first one I'm going to do. Here's pass. This is passing and S none, right? And this one is going to be failing, G fail, and S none. And it's a perfect 50-50 split. That's because given that you study none, you have a 50% chance of passing and a 50% chance of failing. So that's the entire event got split into two. Half the time you pass, half the time you fail. That's on the event S none. And similarly, for studying a little bit, it's like an 80-20 split. So this is like 0.8, and this side is 0.2. And you could label this with G pass, and you studied a little, and G fail, and you studied a little. Is that little piece. Okay. Last but not least, this is what you really want to do, study a lot. Then you get a 90% chance. So this is like 0.9. And this is 0.1. Okay, and this is you pass, and you study a lot. You pass, and you study a lot. Okay, so the probability space is divided into 6 pieces, and you can kind of visually see the rough sizes of the individual pieces, right? Some of the pieces are really small. Like if you fail and study a lot, super teeny tiny chance of that happening. If you study a lot, you're probably not going to fail. Very small chance of this one. On the other hand, the most likely thing is like that you studied a little and you passed. That's the most likely thing. And all of the individual sizes, it really is exactly the same as our tree, right? If you have a creative mind, the tree and this are like the same picture, right? You can kind of see those things as being the same. That's good. So this is like a visual demonstration of the probability space using this area as probability idea. When someone says, please calculate the probability of passing at all, passing can happen in 3 different ways. The law of total probability says you just add up all the different ways it can happen. And so the probability of passing is exactly the area of this little staircase. Right? This staircase is the probability of passing any which way. And it's made of 3 parts. Passing when you studied a lot, a little, or none. What's the area of that staircase? Well, you add up the areas of these 3 rectangles. That's exactly what we did. It's exactly the same thing as we did, but just shown visually. So tree diagrams and Venn diagrams, same kind of picture. Hopefully it makes sense. This is what we were doing at the end of class on Monday, and this is a nice word problem to go with it. Questions or comments about this one? Yeah?
And then if the 2 events that we're comparing are mutually exclusive, then we can just draw one, pick the other, and then...
Yeah, so mutually exclusive in the picture just means they don't overlap, right? That's the only thing it means in the picture. So like there's 6 rectangles, any 2 rectangles are not, they are mutually exclusive because they don't overlap.
What was the situation in last class where you could just draw 2 different square diagrams and then overlay them, and then...
Yeah, so we have like A and not A is a little bit like in our class we have none and a little are mutually exclusive, right? The yellow area and the green area are mutually exclusive. Maybe there's another time that I'm not thinking of right now. Yeah. Okay, this is great, yeah. Independence or dependence. So in this problem, there's no question about independence or dependence. The thing that is true is you will have independence when things perfectly line up. So if it happened to line up like this, and you did the 4 things and it was 2 straight lines, that would be a situation where they're independent. And you can check because the intersection, the little both areas, is the product of the 2 heights, the height and the width. This problem is not about that, but and you can see from the picture that things are not independent, right? Whether or not you study, how much you study is not independent of how much you pass or fail. If I know how much you studied, I can probably guess if you passed or failed with more accuracy, and vice versa. If I know that you passed, then I can figure out what is the chance that you studied, and it's more likely that you studied a lot. So they're not independent in this case. If they were independent, the picture would look like this. Yeah, that's a good point. Okay, there's a whole other genre of Venn diagrams. When you make circles, they're good for other things. This is the one that's good for conditional probabilities because you can split up the rectangles according to the conditional probabilities. All right, yeah, great questions. Anyone else? Okay, we're going to do some more word problems, and I would like the last word problem that we do for the day to be the birthday problem. So that's what I know I mentioned this last week, but now hopefully we'll get there today. Last time, let me remind you of the 2 cards, same suit problem. Oh, well, let me pause this so nobody answers. Okay. So we did this one, I think, on Friday or something. And we had a deck of cards with 52 cards that was made of 4 suits of 13 cards. You're dealt 2 cards. What is the chance they are the same suit? And let me draw the picture for this situation. I think some people were confused by a thing. So I'm going to repeat it quickly. I drew a tree that looked like this. This was like my lazy tree to sort of save time. My lazy tree. It was like this. So you had 13 of each suit. 13, 13, 13, 13. And then I said, okay, you're dealt 1 card. Then you have 12 of one suit and 13 of the others. Right? And then you can either have the same suit or a different suit. And that was kind of like an earn problem. So in the first card, I was like, look, it doesn't matter what you get dealt. In the second card, that's when it starts to matter. And if you're going to be dealt the same suit, you got to pick 12 out of all these cards. If you want a different suit, there's 13 plus 13 plus 13. There's 39 cards that work. That's what I did before. I think some people were confused by this. Let me draw the answers. And I'll draw it one more way so you can see it the other way if you were confused. So this is 12, 12, 13, 13. The other way you could draw it is you could really split it up into the 4 cases. You could say, I have the 4 cases. Either the first card is a heart, diamond, club, or a spade. Okay. And then you could look at the 4 different cases. And you would find that after this first step, the second round is always the same. So you'd have same and different, same or different in each of them. And this is the reason I didn't want to do it, is it's annoying to copy it out 4 times, same or different. And because in the second round it's always 12 over 51 to 39 over 51 in same, different, same, different, same, different, when you add up over all the branches, all these branches are equally likely. You're adding up the same thing 4 times and multiplying by a quarter every time. These 2 things are exactly the same. So last time I did it like this way on top, and I want to keep doing it this way because we're going to add more stuff to it. And if it's harder to do when you have a tree like this, that's big. So that's what we did last time. The answer to the question, what is the probability that they're the same suit? Well, the first card, that can be anything, so a 100% chance on this first branch. And then multiplying down, 100% times 12 over 51 is also 12 over 51. So the answer was 12 over 51. I do also apologize. I realized after class some people wrote 4 divided by 17. If you wrote 4 divided by 17, you also got it right. So good for you. That's what we did before. This is the tree we're doing. We're going to do a harder version of this. So if you don't understand now, you will soon. But this is a good chance to stop for questions. Yeah?
So what if the question was changed and it asked from the very beginning, like, what are the odds of getting 2 diamonds? Would it then be 1 over 4 times 12?
That's right. So if the question said, what are the odds of getting 2 diamonds? Or the question said, what's the odd of getting a club and then anything? Then you would have to use this tree. That's like more detailed. The reason I can get away with the lazy tree is specifically because the question didn't ask me about that. So I think this is a good like life lesson too. Again, with word problems, think about what you want to get and do the minimum amount of work to get to what you want. If you only want to know the probability they're the same, then the actual suit doesn't matter. In a different question, it would matter, and you'd have to do something different. That's a very good point, and maybe that was partially why some people didn't like this way of doing it. I will say that's like a big theme in probability. There's always a really hard way to do it, but there's often an easy way to do it, especially if the question finds its way to an exam or homework or something. There will be an easy way to get it. If you're doing it some crazy complicated way of like trees with like thousands of things, then you probably made a mistake. And there is an easy way to do it. You got to just think of the easy way. Great question. Anyone else? Okay, let's go to the follow-up question, which says, 3 cards, different suits. So before it was 2, what is the probability of 2 cards being the exact same suit? Now I want 3 cards, and I want them to all 3 to be different. So if you have any pair inside your 3 that is the same, that's no good. You want, out of the 4 suits, I want to have three of them in my 3 cards. And I've given you the answer as 39 over 51 times something. Why is the answer 39 over 51 times something? Because the way you do this question is you take the probability tree from the previous question and you add another layer. So if you've understood the probability tree up to the first and the second card, now you can add on the third card. And if you think about it the right way, you can get the answer by just doing one more branch. So I've given you the first branch is 39 over 51. What is the next branch going to be? That's what I want you to do. So fill in the next part of the diagram and try to answer the question. Yeah, what's the probability that the third card is a different, all 3 are different suits? Okay, let me give you guys like 2 minutes to give that a stab. Feel free to chat. Yes, I can put the question back up as well. Let's see. Can I do both? Okay, I'm going to bump it up by a little bit here. I don't have many answers. Let me bump it up to 1.5 minutes. But please put in your guess. Put in 111 if you don't know at the end of 1.5 minutes. You have no idea. It would be 50-50. If you knew for some reason that you knew it was one of those 24 cards, and you're identifying as 50-50, you're like 12 ways this way, there's 12 ways the other way. So 50-50. But I think more accurate to say there's a 12 over something chance for this to happen, a 12 over something chance for that to happen, a 13 over something chance for this to happen. Yeah, exactly. Yes. So it's going to have something to do with it. Did you have a question as well, or can we just say?
I didn't have a question.
Okay. All right, there's like 30 seconds left. Put in what you think. Again, if you have no idea, you can put in 111. If you have a guess, put in your guess. It's better to put in a guess and see that it's wrong than to say you have no idea. You might, even if you have no idea what's going on, you might be able to guess what the denominator is. That's actually not so hard. Even if you don't have a clue, you can maybe figure that one out. Okay, time's almost up. Okay, let's stop the timer. And I'm curious what people said. Reveal what people said. Okay, on the bottom, this is the thing maybe most people got. Even if you're very confused, you might still be able to figure out it's something out of 50. That's because there's 50 cards left in the deck. That's exactly right. So the 71 people, that's almost everybody who said 50. Great job. What about the top? The top, slightly less people, but 55 people said 26. And the right answer is 26, I think. Okay, yeah. So most people got it. Some people were off by 1 with 27. Let's see what that is. Some people said 38. There's sometimes a pattern in probability where you subtract one from the top and subtract one from the bottom. If you said 38, you're over pattern matching. You're seeing patterns where they don't exist. Let's see why it's 26. The reason why it's 26 is we're just going to draw the next part of the branch. And again, on this same suit one, the game is already over. Like we already have the first two cards with the same suit. It doesn't matter what happens in the third card. So I only need to draw this last one. So, and now, when you say same suit or different suit, you should label it a little bit more carefully. Before I had two cards, so same suit or different suit made perfect sense. I would say you can have different than the first two, or like same as one of the first two. Those would be the two branches. So let's say an unseen suit, unseen value. Like that's a completely new value or a unique value, right? Or it could be something we've seen already. Seen already. Okay. So if you want to know if you've seen it already or if it's an unseen value, the thing you got to look at is two of the suits we've seen already, two of them we haven't seen already. So the ones we've seen already, there's 12 of each left. And the ones we haven't seen, there's 13 of each left. Those are the unseen values. So the chance of going to a seen already card is 12 plus 12 out of 50. 12 plus 12 out of 50. And the chance for an unseen value is 13 plus 13 out of 50, also known as 26 out of 50. And so that's the conditional probability of, once you've gotten to the point where the first two are different, the conditional probability if you've seen it already or it's going to be a whole new unseen card, they're 26 to 24 out of 50. And that's why the answer is this product, 39 out of 51. That's the first side of the branch. Then 26 out of 50 is the next branch we added. So I think, close to 60% of people got that right. That's very good. Any questions or comments about this one? So now we're going to do the thing in math where we take the problem and we go to the next level. The next level is what would happen if there was a fourth card or a fifth card and so on. Right? You can imagine doing this for a fourth card and a fifth card. It's like you're being dealt out cards and you keep asking, okay, what if you're dealt a lot of cards and you want them to all be different or the same or something like that. And this kind of tree picture, if you can spot the pattern of what's going on, you can answer the questions for any number of cards. And I claim that that is exactly what the birthday problem is. So the birthday problem, in the first day of class, we said, how many people do you need in the room before two people have the same birthday? But a more specific question you could ask is say, let's say there were 10 people in the room. What's the chance two of them have the same birthday? And that's exactly the same kind of question as, if I deal out 10 cards, what's the probability that two of those cards are the same suit, right? So in the cards, there were 4 different suits. In birthdays, you have 365 birthdays you could be. But otherwise, they're the same problem. There's one other small difference. Let me write this down. So the analogy. So the birthday problem versus cards and suits like we've been doing. Cards and suits. It's like Guns N' Roses, but less cool. Okay. In the birthday problem, each person has a birthday. There's 365 possibilities. Each person has 365 choices for their birthday. Choices. Possibilities? Possibilities. Each card here has 4 choices. So other than that, asking a question like, if I deal out 10 cards, what's the chance that there's 2 of them that have the same suit is the same thing as what's the chance that if you have 10 people, some of them have the same birthday. It's like a deck of cards with 365 possible suits. The suits are labeled January 1st, January 2nd, and so on. So there's 365 suits, and every card has one, and you're dealing out some number of cards. There's one other difference between cards and people in a room, which has some special terminology buzzword that goes with the course that was taught, I think, last week. Does anyone know what the difference is? Yeah. This is the right kind of like tricky buzzword of I'll tell you. Okay, this one is something something, and this one is the same something something, but this one has an out. Blank out blank, and this one is just blank blank. Those are the differences. Yeah. With replacement and without replacement. That's exactly right. So cards are dealt without replacement. So when I deal you 2 cards, I deal you the first card, and then the next card from the deck, I just take it from the deck. So it's not like I deal you a card, you look at the card, I put it back in the deck, right? Once I've dealt you the card is removed from the deck forever, and what is left is without replacing that card. But people, when they walk in the room, the birthday of the first person has nothing to do with the birthday of the second person. It's not like when the first person walks in and their birthday is February 7th, that February 7th is gone from the deck, right? So this one is with replacement. Okay. So this one is with replacement, and there's 365 people, but the probability tree is exactly the same. So your homework before Friday's class is to draw the probability tree for same birthday, different birthday, and draw it 10 layers deep and see if you can find the formula. Same birthday, different birthday. And you can do same, different again and again. ... Can you do it 10 times and find the pattern? And that will let you solve what this is. So we did it 2 layers deep for cards. Now we want to do it 10 layers deep for people. That's what we'll finish up on Friday. All right. See you guys then.